Circle Geometry, Cyclic Quadrilaterals, Part 1. That is what is known as a cyclic quadrilateral. It's a quadrilateral with all four corners, which we usually call vertices, on a circle. Let's look at a property of the cyclic quadrilateral. If we join to the center of the circle, then that angle is twice that by angle at center. And O2 is twice C for the same reason. Now let's do a bit of algebra here. I can add those two and add those two. This must equal that plus that. And I'm going to do a bit of manipulation, so let's just swap the equation around. O1 plus O2, well, those are angles round a point, and I can factorize here. Angles at a point, which means A plus C is 180 degrees. A plus C must always add up to 180 degrees. Now those two add up to 180, all four add up to 360, which means these two must add up to 180. So we have a theorem which says the opposite angles of a cyclic quadrilateral are supplementary, add up to 180 degrees. And it can either be a normal quadrilateral or a funny looking squash quadrilateral, still 1, 2, 3, 4 sides and still all four corners on the circle. So op angles cyclic quad. Let's have a look at some examples. Number 1. X is pretty easy. It's opposite the 78 in a cyclic quad. Op angle cyclic quad, which means it's 102 degrees. Y also. Right. This one here, A adds up with B to give 180, but we don't know B. So does A combine with anything else? Yes, A adds with 101 to give 180 because these are co-interior angles and the lines are parallel. Note, we have to state the parallel lines. That means it's easy enough to find B now because we have its opposite angle in a cyclic quad. And grade 7 geometry tells us to find C. In this case, P is equal to Q, Q is equal to P, R we're not sure of. Well, R plus P equals 180, there's a cyclic quad. So let's start with finding P and Q. We have now isosceles triangle and we know one angle. So therefore, P plus Q must equal the remainder of the 180 by angle sum triangle. Being equal to one another, they must each be half of the 136, so therefore our isosceles triangle tells us 68. So now we have that 68, that 68. Because that's 68, we can find R because they must add up to 180 degrees. Opposite angle cyclic quad. This next one here. X, what is X equal to? Well, it's equal to twice Y. But we don't know Y. So we'll have to start with Y first. Don't mistake this for a cyclic quad. Please don't, but because that point is not on the circle. This has nothing to do with cyclic. But Y is on the edge, and that's a cyclic quad. So we can find Y very easily. Once you know Y, it's straightforward because X is twice Y. Angle at center. Now Z is not equal to anything in this diagram, but Z combines with those other three angles to give you the angles of a quadrilateral, which add up to 360 degrees. Therefore Z is 88 degrees. Let's do a bit more manipulation of the cyclic quad. I've just produced the sides, DC to E. You remember that when you produce a side, you form what we call an exterior angle. Now, C1 plus C2 is 180 degrees, adjacent angle straight line. But A plus C2 equals 180 degrees, opposite angle cyclic quad. So we have these two together there. Now have a look. A adding with C2 to get 180, C1 adding with C2 to get 180. So if C2 was 100, A would be 80, C1 would be 80. So this tells you that A and C1 are equal. Which now gives us another theorem. If a side of a cyclic quadrilateral is produced, the exterior angle formed, so there's the exterior angle there, is equal to the interior opposite angle. So exterior angle, inside opposite angle, because that inside opposite adds up with that there to get 180, and that adds with that to get 180. And we call that exterior angle cyclic quad. Bit of a neglected theorem. People often forget it and use combinations of adjacent angle straight line and opposite angle cyclic quad, but that's reinventing the wheel. So, circle geometry so far. We have the chord theorem, converse chord theorem, which we just call chord theorem. Angle at center, two more angles at center, there. Angle in the semicircle, an extension of angle at center, where we've taken these lines and formed a straight line with them. So the angle of center is 180, so therefore the angle at the circumference is 90. And that's called angle in the semicircle. Then we have angles in the same segment, big segment, small segment. We have angles in equal segments, which is a corollary of this one, or angles subtended by equal chords. And now we have that the opposite angles of cyclic quad add up to 180, so the one with the filled arrow with the one with the filled arrow gets 180, the one with the open arrow, one with the open arrow gets 180 degrees. And finally we have the exterior angle cyclic quad. The exterior angle, by producing one side, the exterior angle equals the interior opposite angle. Let's do some examples. First one, find x, y, and z. Well, what's x equal to? 180 minus z. But if we have a look, there's the exterior angle. Look there, we produced a side, so x is equal to straight 100 degrees exterior angle cyclic quad. Y is opposite the 90 in a cyclic quad. Therefore, it's also 90. And z's either opposite angle cyclic quad or adjacent angle straight line. You can do it by other ways. Here's another set of ways to do it. Z first, adjacent angle straight line, Y 90, opposite angle cyclic quad, and X 100, opposite angle cyclic quad. So there are often many ways to achieve the same thing in geometry. Having a look at the next one here, X you can easily find using angle sum triangle. Now in this triangle we have two unknowns, so it's a problem, but hang on, this is a cyclic quad, so therefore y and 80 add up to get 180. So y is 100, opposite angle cyclic quad. Now we have an angle sum triangle again, so we find z is 25. The third one, x, well, this is a cyclic quad there. And have a look, one side produced. So the exterior angle formed equals the interior opposite angle. So therefore, x equals 120, exterior angle cyclic quad. O, the center is on the line. Therefore, this is a diameter. Therefore, this is an angle in a semicircle. Remember, an angle in a semicircle, 90 degrees. So y is 90 degrees, angle in semicircle. And z, well, we have an exterior angle triangle now, 120, and this triangle here, producer side, 120 equals those two added. So z is 30 degrees, exterior angle triangle. X, straight simple geometry, we have one angle in an isosceles triangle, so we can find x. 35. 180 minus 110 is 70, so these two add up to 70 and they're equal. So we halve 70. We have nothing in these triangles, but hang on, y and 110, they're opposite in the cyclic quad. Therefore, y is 180 minus that one. Opposite angle cyclic quad. Now we have the top angle in an isosceles triangle, so we can find z. 180 minus 70 gives 110. Halved gives 55. And we have, may I dare to be naughty and say a bow tie? There we are. We have the angles in the same segment. So therefore, the tips of the bow tie equals, so W equals 55. And its angles in the same segment. Number 5. X is pretty straightforward. There we are. We have it again. The tips are equal. So x equals 35 degrees, angles in the same segment. Y, well, y we can find there, this triangle here, we produced a side. There's the exterior angle, equals that plus that. So therefore, y we can find by exterior angle triangle. And of course, the tips are equal. Here's the bow tie. Here's the angles in the same segment again. So therefore, z also equals 66, angles in the same segment. Straight away I've done that. It's quite useful to do that immediately. One of the things, I see a diameter, so straight away I know 90 and 90. Right. So x is equal to, well, what is x equal to? Equal to that one there. Have a look here. Angles in the same segment. There we are. X is equal to that angle. We know that's 90, so we can find x easily. QSR equals 29 degrees, and the reason is angle in semicircle. That doesn't mean it's 29 because of the angles in semicircle, but it means it's 29 because 61 and that give you 90, which means we know x. Angles in same segments. And now we have a triangle with a produced side, so Z is the exterior angle. Oh, we're going a long way around. That's fine though. You see 35 degrees, therefore 35 by angles in the same segment. Those add up to give 64. There's the exterior angle cyclic quad. Cyclic quad. Producer side, the exterior angle equals the inside opposite angle. There we are. Number 7. Yo. If you have a look here, be careful, they're not all, but here's some angles in the same segment. That's not the same. But if we have a look here, we can get x straight away. The angles in the same segment. X is 50 degrees, angle in the same segment. Now, here's a cyclic quadrilateral. Keep your eyes open for them. There we are. 4 corners on the quad. That's 50, so the opposite angle, 180 minus. So therefore we get y equals 130 degrees. Now we have an isosceles triangle with knowing one angle. So we can find z easily. W, well, have a look here now. Be observant. You see we have a bow tie. There it is there. So the tips are equal to one another by angles in the same segment. Well, number 8. Now here you're going to have to look very, very carefully. This is something we haven't used yet. A hint to you is that line equals that. This angle is subtended by this line. This angle is subtended by this line. Do you see that that must equal that? By that corollary which said angles subtended by equal chords are equal. X equals 34 degrees. Angles subtended by equal chords. There we have it. Now, we have to find y. In order to find y, we're going to need to get into this other quadrilateral somehow. So we say, well, is there anything in this quadrilateral which is equal to something in that one? They're both cyclic quadrilaterals. Well, have a look. This one here is an exterior angle of this cyclic quadrilateral. We produce a side. So therefore, that exterior angle equals the inside opposite angle. So therefore, we have that angle there, FCD, is 68 degrees. And that gives us the value of the opposite angle y. There we are. Now at this stage we're left with this one, and the only way it can work is if we know that or this. So we have a look and say, well, in this triangle, in this figure here, this circle, do we know the size of that angle? Well, there's your hint, there's a diameter. Yes, that there is 90 degrees, angle of semicircle. And that makes Z 90 degrees, exterior angle, cyclic quad.